Hello and welcome to 9.5 Alternating Series, another one of the fun sections. I think 9.4 is pretty fun. This is kind of fun too. Alternating Series is a series whose terms alternate in sign from positive, negative, or negative, positive, negative, positive. Okay, theorem 9.14, alternating series test. Let a sub n be positive, so all the terms are positive. This is before we might apply a negative that would occur as part of the series. The alternating series n equals 1 to infinity of negative 1 to the n a sub n and negative 1 to the n plus 1 a sub n. Only difference here is the first term positive or negative, and it alternates from there. The series converge if the two conditions are met. The limit as n goes to infinity of a sub n is 0, and a sub n plus 1 is less than a sub n. So they're getting smaller every time, and and the limit's going to 0. So you might be saying, wait a second, Jeff. I thought the harmonic series, which has a limit of 0, doesn't converge. And you'd be correct in saying that. I mean, it satisfies these two conditions, harmonic series, 1 over 1, 1 over 2, plus 1 over 3, plus 1 over 4, and so on. However, it misses the first condition that it's not alternating. So the alternating harmonic series would indeed converge. So this is the key to it. Getting positive, negative, positive, negative, positive, negative. So determine the convergence or divergence of the series. So for this first one, our a sub n is 1 over n. A sub n plus 1 is 1 over n plus 1. 1 over n plus 1. Now, 1 over n plus 1 is going to be less than 1 over n because it has a bigger denominator, makes it a smaller fraction. So a sub n plus 1 is less than a sub n. The limit as n goes to infinity of 1 over n is 0. Because it's alternating, and I realize this is harmonic series, because it's alternating, this will converge. So this converges by the alternating series. Cool test there, alternating series test. We'll look at example 2. I'm just going to scroll this up to that point. So in this next example, the a sub n is n squared over n squared plus 5. Now if you take the limit as n goes to infinity of n squared over n squared plus 5, you get 1. That limit is not 0, so this will not converge by the alternating series test. So it diverges since the limit is not 0. That's it. Let's go to page 2. Okay, for example 3, it says to approximate the sum of the series by using the first 6 terms. Okay, so our first term is going to be 3 over 1 squared, which is 3. Our second term is going to be 3, let's just say negative, because the negative 2 plus 1 is 3, negative 1 to 3 is negative. 3, so negative 3 over 2 squared, or negative 3/4. A3 is going to be 3 over 3 squared, which is 1/3. A4 is going to be negative 3 over 4 squared, which is negative 3/16. A5 is going to be 3 over 5 squared, which is 3 over 25. And A6 is going to be negative 3 over 6 squared, which is, that could be reduced, it's going to be negative 3 over 36, or negative 1 over 12. So if we add these up, our S sub 6 is going to be 2.4325. Okay. Now, this is an important theorem here. Not really big into remainders or approximations of function or approximation rules, but theorem 9.5 is really useful here. Alternating series remainder. If a convergent alternating series satisfies the condition that a sub n plus 1 is less than a sub n, and we said in this case they're getting smaller every time. If you don't worry about the negative, each term, each successive term is getting smaller. Then the absolute value of the remainder r sub n involved is approximately the sum s, involved, I should say n approximating the sum s by s sub n is less than or equal to the first neglected term. That is, s minus s sub n is the remainder, and that's going to be less than the first term we don't count. So in this previous example, which term did we not count? We stopped after the 6th term, so we didn't count the 7th term. So from here, our a sub 7 was going to be 3 over 7 squared, which is 3 over 49. So that s, absolute value of s minus 2.4325 is going to be less than 3 over 49. So negative 3 over 49 is less than s minus 2.4325, which is less than 3 over 49. So adding 2.4325 to each side, we have 2.3712 is less than s, less than 2.4937. We know that the actual sum is between these two values. That's how this is useful. We have a bound for that sum, the actual sum. Okay. So that's the application of that one. Let's do another one, another application for this. Example 4 is the application of theorem 9.15, the alternating series remainder. I need to clear the board here. Okay, this says use theorem 9.15 to determine the terms required to approximate the sum of the convergent series with an error less than 0.001. Okay, so what we want is s minus s sub n, the absolute value, to be less than 0.001. So that we want a sub n plus 1 to be less than 0.001 is what we're after. So it should say less than or equal to it. So we drop off the alternating part, the negative 1 to the n. We have 1 over 2 to the n factorial needs to be less than 0.001. So let's try some values. If we do n equals 3, we have 1 over 2 cubed times 3 factorial, and that would be approximately 0.0026. So that's not quite there. Let's do n equals 4. That'd be 1 over 2 to the 4th times 4 factorial, which would be approximately 0.0002604, and that is less than 0.001. So it works for n equals 4. So we don't have to go that far. Notice this starts at n equals 0. So we can do the sum as n goes from 0 to 3, or we can go to 4. We could probably just stop at 3, of negative 1 to the n over 2 to the n factorial. So that's going to be 1 for the first case, for n equals 0, minus 1 over 2 plus 1 over 8, because 2 squared is 4, 2 factorial is 2, that's 8, minus 1 over 48 plus 1 over 348, and our approximation is 0.607. So we have 5 terms here. Okay. We're on the last page. So I'd pause that if you need more time. Theorem 9.16, absolute convergence. If a series some absolute value of n converges, then the series itself converges. So we're talking about an alternating series essentially. If you're able to get rid of the negative part and all those things added up with the positive way converge, the overall thing will converge. Definition of absolute and conditional convergence. The series sum of a sub n is absolutely convergent if the absolute value, the sum of the absolute value is convergent. And the sum is conditionally convergent if the sum is convergent but the absolute value diverges. The sum of the absolute value diverges. So it's conditionally convergent if you need the absolute, if you can't have it converge with the absolute value, if you need that negative in there to cancel terms out. Okay, determine whether the series converges conditionally or absolutely, or if it diverges. Okay. So well, first of all, look at the following. N goes from 1 to infinity of 1 over n plus 1 squared. If we get rid of this negative 1 to the n plus 1, that would be the sum, as n goes from 1 to infinity, of 1 over n squared plus 2n plus 1. This converges by comparison to the sum 1 over n squared, which converges by the p-series test. So, therefore, sum n goes from 1 to infinity of negative 1 to the n plus 1 over n plus 1 squared converges absolutely. So by dropping the negative, it converged. It still converged, therefore it's absolutely convergent. So dropping the alternating negative, excuse me. We're going to go on to our last example from this section. Same thing for this one, and will it converge absolutely? Will it converge conditionally, or will it diverge? So we can rewrite this as n goes from 0 to infinity, negative 1 to the n over e to the n squared. So let's look at the sum. N goes from 0 to infinity, 1 over e to the n squared. Now we could express this as, so I drop the negative off. I'm looking at it so I can hopefully get absolute convergence. N equals 0 to infinity of 1 over e to the n power I think I'm doing that backwards. Okay, so e to the n squared. You have a good way to represent this. Okay. I can't say e to the n. I could say e to the n times n. Which should be 1 over e to the n, like that. There we go. Now this represents this is similar to a geometric series. And 1 over e to the n is going to be less than 1 for n being greater than or equal to 1. And we have that case, or even less than or equal to 1. I'll just say, go with that. After the first term, they're always going to be less than 1. For that first term, it would be e to the 0, which is going to be 1. So, the sum n goes from 0 to infinity of 1 over e to the n squared will converge. Therefore, by geometric series. Therefore, the sum as n goes from 0 to infinity of negative 1 to the n over e to the n squared converges absolutely. Okay, and that's the end of 9.5. So please send me your questions, and I'll see you guys online. And you might want to pause here if you want to write more of that down.